Hello everybody, we're getting ready to do lesson 11.1 part 2 classwork today for pre-calculus math. And for today's classwork you have 2 points go into your notebook, and 52 points that will go on to your classwork sheet, which you should have out in front of you now. Name, date, period, and then due date for onliners and homeschoolers. And today's bell work, teachers and students. Simplify these rational expressions here for 77, 78. Simplify the rational expressions over here. And give your students about 5 minutes. Teachers, pause your video for 5. See you in 5. Okay, welcome back everybody. We're going to simplify this rational expression here. So to do that, we're going to factor out. We're going to break this down to 2 binomials. Break this down into 2 binomials. And we have this here. These will cancel. 3x minus 1 times 5x plus 4 over 3x minus 1 times 5x plus 2. These cancel. And then we end up with 5x plus 4 over 5x plus 2. And x cannot equal 1/3 for down here. So that'd be the 77, and then for 78, you do the same thing here. Break it down into 2 binomials, x minus 6 over x minus 6 multiplied by x minus 1. These cancel here. You end up with x minus 6 over x minus 1. And in this case here, they're saying x cannot equal 6, which, yeah. What about x cannot equal 1 either, I would think as well. But those are your solutions for today's. Into today's lesson, we go into in example 3 from the previous lesson. Note that f of x has a limit as x goes to 0. This was it here in example 3. Even though the function is not defined at x equals 0. Even though it's not defined at x equals 0 here. You have a 0 up here. And then 0, you take the radical of 1 minus 1, that would be a 0, so it would be undefined. This often happens, and it is important to realize that the existence or the non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. So take note of that. And let's go into an example now of that. Using a graphing utility to estimate a limit. So estimate the limit here. Limit as x goes to 1 for this expression here, x cubed minus x squared plus x minus 1 over x minus 1. So let f of x equal this here. This is what it is. F of x equals that expression. Create a table that shows values of f of x for several x values near 1. Here we are here. Here are your values near 1. And for 1, there you get an error message for that. It appears that the closer x gets to 1, the closer f of x gets to 2. So we approach 2 from both sides here, and as we get closer to 1. So you can estimate the limit to be 2 for this situation here. You can just continue these trends here, and you would assume that when x equals 1, y would equal 2. Using a graphing calculator to graph f of x equals x cubed minus x squared plus x minus 1 over x minus 1, using a decimal setting, you'll get this parabola here as shown. And then that point there, use the trace feature to determine that as x gets closer and closer to 1, which is right here, f of x gets closer and closer to 2, which is right here, from the left and from the right. So from the left, and then from the right here. So it's safe to assume that from the well. You can estimate the limit to be 2. As you use the trace feature, notice that there is no given value for y. There is no given value for y when x equals 1, and that there is a hole or a break in the graph at x equals 1. So there is a hole there when x equals 1. Okay, so let's try another example here. Use the table feature of a graphing utility or calculator to create a table for the function and use the result to estimate the limit numerically. Use the graphing calculator to graph the corresponding function to confirm your result graphically. So we have this limit here of as x goes to 1 for x minus 1 over x squared plus 2x minus 3. So for that limit there, this is our original expression, and then you can reduce this, simplify this to equals 1 over 4. And then when you graph this thing here, you have an error here. When x equals 1, you have an error, but it equals 1 over 4.25. You approach it from this side, and you're close to it on this other side as well. And then the graph of it would look like this here. So you have a hyperbola here for this expression, and it approaches 1.4 here as x approaches 1 here, which would be over here. It would approach 1/4 here. See 1.1. See, as you go further here to the right, see here, as you go further to the right, it kind of falls back from the 0.25, which is right about here. It's almost like a horizontal asymptote for this limit. And then down here is similar, but you have as x approaches -2. So you have a little different situation there. That's your independent practice there, students, so do that. Moving on, example 5, using a graph to find a limit. Find a limit of f of x as x approaches 3, where f is defined as f of x equals 2 when x cannot equal 3, and f of x equals 0 when x equals 3. So you have two different conditions there. Because f of x equals 2 for all x other than x equals 3, which is right here, and because the value of f of 3 is immaterial, it follows that the limit would be 2. So this would be the graph of this function here with a hole at x equals 3. So overall, the limit would be 2. So you can write the limit as x approaches 3, f of x equals 2. The fact that f of 3 equals 0 has no bearing on the existence or value of the limit as x approaches 3. For instance, if the function were defined as f of x equals 2, x cannot equal 3, f of x equals 4, x equals 3, then the limit as x approaches 3 would be the same. It would be the same. Okay, let's try another one here. Find the limit if it exists as x approaches 2. So as x approaches 2, x cannot equal 2, x equals 2 in this situation there. So the limit of f of x equals 3 as x approaches 2, this would be your limit here. You have a hole here when x cannot equal 2, then when f of x equals 1, which would be here, x equals 2, so you would have this here. It would drop out for that one down here. So the limit of f of x equals 3 is as x approaches 2. Comparing left and right behavior, show that the limit does not exist. So we have a limit here as x approaches 0 of the absolute value of x over x. Consider the graph of the function given by f of x equals absolute value of x over x. This would be it here. So you would have holes here at the on the y-axis. So you have it approaching from the right and then from the left here. See that for positive x values on this side, you have the absolute value of x over x would equal 1. X has got to be greater than 0. So for that to happen, it would equal 1 because you have the horizontal line here. And then down for that other side of that limit, and for the negative values of absolute value of x over x equals -1, it would be down here. X would be less than 0, so you'd have a drop off here on your limit. This means that no matter how close x gets to 0, there will be both positive and negative x values that yield f of x equals 1. And f of x equals -1. This implies that the limit does not exist, because at this one point here, it kind of is discontinuous here. There's no continuity here with this. And limits always stress continuity, and this shows discontinuity. Okay, let's try one. Use the graph to find the limit if it exists. If the limit does not exist, explain why. So we have this limit here as x approaches -2 for absolute value of x plus 2 over x plus 2. So the graph of that is here. So again, you have a discontinuity here, which is kind of a dead giveaway. Does not exist because f of x equals absolute value x plus 2 equals -1 to the left of -2 and equals 1 to the right of -2. So you have a you have an ambiguous kind of situation here when it approaches 2 and -2. It has two different values for it. To the left of -2 and equals 1 to the right of -2. So you have an ambiguous kind of solution there for this limit. Unbounded behavior. Discuss the existence of the limit as x approaches 0 for 1 over x squared. So note that as x approaches 0 from either the right or the left, f of x starts to increase here without bound. This means that by choosing x close enough to 0, you can force f of x to be as large as you want. For instance, f of x will be larger than 100 when you choose x that is within 1/10 of 0. That is, 0 is less than absolute value of x is less than 1 over 10, and this becomes f of x equals 1 over x squared is greater than 100. So when you get closer to 0, the larger your f of x value becomes. Similarly, you can force f of x to be larger than 1 million as follows. So we have, again, 0 less than absolute value of x, less than 1 over 1,000. And this because f of x equals 1 over x squared is greater than 1 million. When you have this situation here, the absolute value is 1 over 1,000. It would become 1 million. So it would increase further and further as you get closer to 0. Because f of x is not approaching a unique real number L as x approaches 0, you can conclude that the limit does not exist. So let's try another one of these. Use the graph to find a limit if it exists. If the limit does not exist, explain why. So we have here the limit as x approaches 1 here, down here, and up here for 1 over x minus 1. If the limit doesn't exist, explain why. And instead you have this down here as well. So the limit does not exist because f of x does not approach a real number as x approaches 1. So you have, it decreases this way and it increases this way as it approaches 1. So it's rather ambiguous to say the least. And that is 11.1, Part 2, Pre-Calculus Math classwork. My email is animatedpowerpointmathvideo@aol.com for course materials and/or questions. Thank you very much.